Okay, so we left off finding out where our critical points are. Notice this is a local max, this is a local min. Of course, you should be able to tell me that your function f is decreasing from -3 to 6, and f is increasing from -infinity, -3, and then 6 on. Okay, what would happen if I want to find the inflection points? Okay, so from your table, you learn that your inflection point should pop up when your second derivative is equal to 0, right? So first derivative equal to 0, that's your max min. Second derivative equals 0. This is where you expect your inflections to come up. All right, so let me look at my original function, and I'm going to just write down what I had before. This was 2x cubed minus 9x squared minus 108x plus 2, right? And we already took the derivative and found out that was 6x squared minus 18x minus 108. Okay, let's take another derivative. So in order to do the second derivative test, the very first step is to take the second derivative. So f double prime of x then equals 12x squared minus 18. And then the step 2, notice this should look familiar, set the second derivative equal to 0. Right, so the steps are very similar to the first derivative test, or first derivative process, I should say. Let me make a correction. I can actually see where the error is. This isn't 12x squared, this is just 12x, right? The 2 comes down, that's 12, 1 less power gives me a 1. So that's to the first. So 12x minus 18 is equal to 0. And then step 3 is to solve for x. So let's see, 12x minus 18 equals 0, add 18, add 18. So 12x equals 18. Then you're going to divide by 12, divide by 12. So then an x equals 18 divided by 12, which you can always convert that to a smaller fraction if you so decide. 3 over 2. Okay, so either you can put 1.5 or 3 over 2, whichever way you want to do it. All right, so this is an inflection or a question mark, right? So why? Because it's where the second derivative was equal to 0. Okay, so what that allows me to do is to set up another number line. But this time I'm going to pay attention to the second derivative. All right, so let's see. Here's my number line. And right here, I have 3/2, 1.5. Okay, now this is where things get interesting because now I'm using the second derivative to tell me what the original function looks like. Okay, so a number to the left of 1.5 is, well, we just use 1. And to the right of 1.5, let's use 2. And I'm going to plug them into the second derivative. This is what you have to keep in mind. This is called the second derivative test. All right? So let me go back to my second derivative because I don't want to get distracted. Look, here's my second derivative right here. So we know that f double prime of x in general equals 12x minus 18. Okay, and let me clarify something really quickly. Notice the second derivative is just the derivative of the first derivative, right? So this is f prime, so the derivative of that is 12x minus 18. All right, so we want to plug these 2 points, 2 x values into our second derivative. Oops, minus 18. So this equals -6. Negative spit out there. At 2 equals 12 times 2 minus 18. So it's 24 minus 18 equals positive 6. Positive value is spit out there. Right? So watch closely. If the second derivative is negative, if you look at your table, it means your original function is concave down. If your second derivative is positive, it means your original function is concave up. Okay? F double prime positive, F concave up. Please look this up. F double prime negative means F is concave down. Right? So I'm still using that table. That table comes back to haunt us. So I'm going to go back to the work that we did on the very first video and remind you that when we did the first derivative test, this is what we got. But the second derivative test always adds to the first derivative test. So let's see. This says 3/2, which is somewhere in here. All right. And we expect this to be an inflection point. You can see it, concave down to concave up. So this is an inflection. Okay, so right here. All right, so let me show you what's happening. Okay, on this graph, we expect to be concave down all the way up to 3/2. We still have to pay attention to the arrows. Do not neglect the arrows, right? We expect a max right at -3. So we gotta honor that. Right, so that's what your function looks like. And then after that, look, it's right here, you can see it. You would expect your function to be concave up. You can't ignore that at 6 you have a minimum. So you're paying attention to that. I'm doing a really poor job of graphing this. There you go. Right, so this is generally what your function looks like. Let's see, if I can show you a sketch of your original function, and I actually have in your notes already. So let me see if I can get my hands on one of those. Here we go. Right, it has a bunch of writing on it, but look, this is the actual graph. Let me show you this one right here. Right, so you can see right here. Okay, so if you can look where the pin is, ignore the parabola. We're only looking at the wave. Look, you have a local maximum right here at x equals -3, and then right over here at 1.5, you have an inflection point, and your function is concave up thereafter. Right, so what I sketched out here is very similar to what the actual graph looks like. You can always do it in your calculator to give yourself a better idea of the appearance of f of x, and I encourage you to do so. Okay, so if you guys can go back to those problems that you did, those 5 problems I suggested that you do, can you apply the second derivative test to that? It will give you a better understanding.